Thank you, and thanks everyone for tuning in. So I would like to point out a few people who really lifted me onto this topic, and that's Fernando Tornos, who's an economic geologist, and John Hanchar, a geochemist. And they were basically inviting me to come along to a field trip, which really enriched my perspective of geological systems and led to an interesting collaboration in the years that followed. And that's what I'm going to be presenting to you today. Let me see. There we go. So the research themes of my Magma Matters research group, which is sort of a bit of an odd hybrid split between the University of Glasgow, where I was a lecturer before, and ETH, where I'm now at, looks at all sorts of different topics where magma really matters. That goes anywhere from the global scale of planetary differentiation and evolution to the local scale of volcanic activity and the topic of today, mineral resources. And the thing that brings all of the research in our group together is that it's all about multi-phase flows. And by multi-phase, we typically refer to the phases found in magmatic systems, which are solids, liquids, and gases. And depending on their relative proportion, the flows that result can fall into quite different regimes. For example, for solid-rich magmas, or basically partially molten rock at low melt fraction, there's a liquid which is typically a silicate melt that can percolate through the wetted grain boundaries, which you can see here in a micro CT image. And the solid deformation, the solid matrix can also deform, which leads to some interesting nonlinear phenomena. So that's part of the work that I've done previously and that we're doing now surrounds porous flows. Then the opposite end member, if systems are liquid rich, the silicate melt, for example, can become the suspending phase, which suspends crystal particles and gas bubbles or other fluid bubbles. And those systems tend to be low viscosity, so they can be vigorously convecting, and the suspended phases can settle down or float up depending on their relative buoyancy contrast. So really, this is the unifying theme of all of the research that we do. And in particular, we address this with a class of models that some of you might be familiar with, go under the title of continuum mixture models, because what we do in order to resolve the processes in these systems is that we don't attempt to resolve them at the actually physically relevant scale, which is at the scale of the microscopic phase constituents like crystals or mineral grains, melt films, fluid droplets, etc. But instead, take averages over a larger area of that microscopic topology and describe the average velocity, average pressure, average chemistry of individual phases in that mixture. And those average properties are expressed as continuum fields. And essentially, you can imagine there to be a stack of continuum fields, which each represent the behavior of one of the phases. They are collocated, so they can all exist at the same point in time simultaneously, and they interact with each other. So in addition to having material and energy fluxing through the material of each phase, energy and material can also be transferred between the phases with things like phase change reactions, etc. Just two quick examples to show you what that work can look like, because this is a modeling seminar and you might be interested. So this is one example of a porous flow model that I did back in my day working as a postdoc at Oxford, where we're looking at the reactive transport of melt beneath mid-ocean ridges. So here you're looking at a vertical cross-section across the ridge axis with the two plates spreading left and right outside the domain, and the mantle upwelling in the middle through the bottom boundary. The top image shows a slope spreading ridge, and the lower one a more intermediate to fast one. And here you can see this anastomosing pattern of channels emerging, and those channels are actually a dynamic consequence of reactive melting, where a volatile ridge melt that melts deep down beneath the mid-ocean ridge system percolates upwards by porous flow, and as it encounters the depths where anhydrous minerals become soluble, the place of the largest influx of volatile ridge melt picks up the most additional melting of anhydrous minerals, and thereby creates locally high permeability, so something like a corrosive channel in the mantle, and that channelizes the melt. So These systems can become really fascinating if we're considering the interaction of reactions with rheology. Another example is of the opposite end member, suspension flow. This is from a study of a student who I worked with at Stanford, Janine Birnbaum, who was looking at lava flow convection on Mount Erebus in Antarctica. In this model, we had a steady influx of bubble-rich magma coming in the bottom of the lava lake. This is now on a completely different scale, so rather than hundreds of kilometers, this is now on dozens of meters. And that bubble-rich lava streams to the top under its buoyancy, then passes its bubble content onto the atmosphere, and the now denser and degassed magma sinks back down. And this is all modulated by a complex rheology, which is stiffening when crystals start coming up into the lava, and crystals come up because the lava is exposed to the cool walls and the cooling surface of the lava lake. And so here again, I want to stress the complexity and non-linearity of these systems. Even though we're feeding in a steady stream of bubble-rich lava from the bottom, the flow pattern, as you can see, is episodic and time variable. And that actually, we could relate that directly to surface observation of Mount Erebus lava lake. And if you're interested in this class of models in general and this, sort of the foundations of the work that our research group is doing, I would like to point you to this paper, which is sort of the grand theory framework on which I tend to build my models. This is a work that I published together with Jenny Zuccali at Stanford, where we really we went out to try and formulate an internally consistent and broadly applicable model framework for magma transport processes from melt sources in the mantle to emplacement near the surface that is applicable to the entire spectrum between porous and suspension flows, including the mush regime in the middle. That is applicable to 2, 3, or even general N-phase mixtures and flows, where each of the phases can be some general compressible viscous fluid, and that includes solids represented as highly viscous fluids. So this is just for the nerds among you who might want to do that to themselves. And that brings me to the actual topic of the evening. Why, as a modeler or as an earth scientist in general, would we want to study orogenesis? And this might be preaching to the choir, but I think it's still good to remind ourselves of why this is a really important and growing topic. And this is all to do with the green energy transition. A lot of government and intergovernmental bodies have made CO2 net zero emission commitments that are going to take effect over the next 5 to 30 or 50 years. And in order to be able to fulfill those commitments, that would require a massive electrification of the energy sector, transport industry, waste management, farming, etc. You're all familiar with the IPCC scenarios, where basically if we don't really do anything, we're headed for a world that is potentially warming to a degree where it is difficult to judge the consequences, and some of the more extreme consequences would be a high risk and hazard to life on the planet, not just for humans. And if we want to limit this to something that appears more manageable, we don't just need to stabilize our annual emissions, but we need to dramatically reduce it on a time frame of a few decades. At the same time, you can see that the trend up to now was that CO2 emissions were increasing at a rapid rate. And there is currently no trend to indicate that that is turning a corner soon. So we stand in front of a massive challenge. That challenge is exacerbated by the fact that not only is it hard enough to just flip around all of our industry and energy sectors, etc., but it is that if we were able to do that, the demand for metals, for everything from electric engines to batteries, computer chips, the huge magnets that are used, for example, in wind turbines, etc., demand for those metals will grow rapidly. And there's a big question about whether or not resource production can keep pace, because as you are all well aware, metals don't grow on a farm, they have to be mined. And so new resources do need to be found and developed. And I'm showing a bit of data here from a presentation that Adam Simon gave at the HU Fall meeting this is the wrong year. This is obviously in 2022, just the end of last year. If those of you who have credentials to access the HU recordings, I highly recommend that you go and watch this talk, and also the talk that I put in the box here. I can also put that link in the chat afterwards if you're interested. Both of these have basically the same message. They're really excellent talks about how big the challenge is going to be in order to supply metals for the energy transition. And actually, the bottom line is that if we look at the supply gap that is waiting for us just over the next decade, some of the most important elements like lithium and cobalt and graphite, which are really important for electric car batteries, we basically have known and developing resources that cover just about 10% of the demand that we're going to need. And what we all know is that if the demand by far outstrips the supply, then what happens? Prices go up. And if prices go up far enough, we will simply not be able to afford the energy transition. And so this is a really big problem. And so a lot of people are starting to look into, well, where would we find more resources? How can we identify them in a timely manner, etc. And one of the examples of that some of you might have just recently seen in the media is that there was a what was touted as a huge rare earth metal discovery in Arctic Sweden. What happened is basically that there was a well-known iron ore deposit in KIRUNA in northern Sweden, which had been mined for quite a while. And it happens to be a type of iron ore which is known as magnetite-apatite deposits. I'm going to say more about that later. And it's named like that because the magnetite typically co-occurs with apatite, which is a phosphate mineral which can contain quite significant fractions of rare earth elements. And so accompanying this KIRUNA iron ore is actually a large body of rare earth element enriched apatite. This is by far not a new discovery, but it's just that the mining company has now realized that some money can be made. Rare earth elements are going to be in high demand. And so now it seems to be worthwhile to actually develop that mine by drilling a long shaft over from the existing iron mine over into that rare earth element deposit. Now, why do I bring up this example? That's simply because KIRUNA deposits are actually the type deposit for a whole class of magnetite-apatite deposits. These deposits tend to present as massive magnetite bodies. So those are massive bodies consisting of more than 90–95% magnetite, which in some instances is oxidized to hematite, depending on later alteration. These massive magnetites tend to present with intrusive contacts, but you can also take on extrusive characteristics, so such like magnetite-rich bombs, ash, etc. And often is also found in the form of magnetite, diopside, apatite, and hydride-bearing assemblages that have very large crystals like pegmatites. I have a handpiece at home, which is like apatite crystals, the size of an arm. What really brings all of these deposits together, in addition to their common geological presentation and mineralogy, is their iron and oxygen isotopes. Obviously, because a lot of magnetite is involved, those are good oxygen systems to use to characterize these deposits. And what you can see in this collection here is essentially the isotopic signature of a number of these KIRUNA type magnetite-apatite deposits. And in particular, this little red area here is KIRUNA itself, and Laco, which we're going to talk about, is up here. All of these fall into the corner, which indicates magmatic conditions. So that means high temperatures and the mantle type signature of the isotopes. If we're moving towards the left in that diagram, we're coming more to conditions that are identified as high temperature hydrothermal systems, often associated directly with magmatic activity. And then if we go downwards in this diagram, we come to low temperature hydrothermal systems, which can often be found sort of as a late stage hydrothermal alteration that overprints some parts of these systems. But really what this plot indicates is that these different deposits found all around the world are actually bear indicators of a common origin. However, that origin isn't by no means clarified, because whatever the nature and source was of that stuff that got emplaced as magnetite is very debated. And depending on what people believe that original ore liquid to be, the mechanics of emplacement can become a very tricky problem as well. And this is what brings us to El Laco. For that, we travel to the Atacama region in Chile. And here's just a few impressions of that field trip that John and Fernando, you can see in the photo here, took me on. That's already back in 2016. I can't believe it's been that long. If you have a chance in your life to travel to the Atacama region, I highly recommend it. It is one of the most impressive places I've ever seen. For example, the view up here, which really looks like some foreign planet, is taken from the top of El Lascar volcano on 500 meters. And it's just absolutely mind-blowing. But this region isn't just known for its stunning desert landscape, but it's also one of the most active mining areas in the world. And for example, here is one of these magnetite-apatite deposits, which is being mined in a huge open access mine, open pit mine. But really what we went there to see is this kind of rock. And if you put yourself in the shoes of a sort of an undergraduate geologist on a field trip, trying to identify their first rock, if you would hand them one of these and they would observe it's dark colored, small grained, vesiculated, a dense rock found on the flank of an arc volcano. You'd be forgiven if your first guess was this was a basalt, because to all intents and purposes, it looks very similar. The giveaway really is if you hold a magnet against it, because it's magnetic. And this is exactly that material I was talking about, which is upwards of 95% iron oxide, mostly as magnetite, sometimes as hematite. So this is a very curious material. It's not what you would intuitively expect to find. So here, a few more images of the geological characteristics of the El Laco deposits. Here you can see a distance view of El Laco, and indicated here and over there are two of these deposits. They're sort of on the flanks on about the same level around the volcano. They look like vesiculated lavas. They also form breccias with sort of angular clasts supported in a matrix of that same magnetite-rich material. Here it's written as MRT for martite, which is the hematite polymorph of magnetite, so that's the alteration product. Then there's large lava flow-like deposits which have meter-scale gas escape pipes going through, sort of like large merged vesicles. And then there's tephra layers, which have grain sizes anywhere from bombs to scoria to ash. Apologies. And in some of the vesicles, there's late-stage hydrothermal magnetite with really beautiful euhedral shapes, which show these sort of triangular pyramids. So to all intents and purposes, these ore bodies look like lava flows and ash beds. So basically the product of extrusion or explosive or effusive extrusion. So that would suggest that we're looking at a pressure-driven extrusion of some bubbly liquid. And because of the location on the flanks of the volcanoes, it has been interpreted that might be coming up through collapse fractures of the volcanic edifice. But what would that liquid be? How do we get to a liquid that is so rich in iron? And if in fact we have a liquid that is almost entirely iron oxide, that would be a very dense liquid. So how would it actually arrive at the surface? And that was really what puzzled John and Fernando. And that's why they brought me along to basically have the second opinion of a fluid mechanicist on the problem. And I was indeed puzzled at first, but we worked something out, which is what I'm going to show you. So just a little bit of regional context. So we're in very near the place where Chile, Bolivia, and Argentina meet. So this is El Laco here, near the city of Calama. And El Laco itself is found in sort of the corner between two fault systems, one of which is a thrust fault linked to the subduction arc, and the other one is an old left lateral lineament. Just around El Laco, here you can see a false color image of infrared Sentinel-2 imagery. So this is it's a nice tool to look at the surface geology without having to draw a geological map, because essentially there's no vegetation. What you see from the satellite is rocks. And it just so happens that these rocks take on different colors in false color infrared. So these sort of reddish, yellowish colors are solaris, or big salt lakes, which are indication of sort of a basin and range style local crustal extension in northeast southwest direction across the Laco. I'm going to come back to that later on. Looking a little bit closer to El Laco itself, this is a simplified geological map where in green you can see unaltered volcanic deposits. So that's the normal andesite that El Laco is erupting most of the time. The yellowish units are at times heavily hydrothermally altered andesites, and in a black and gray are the ore deposits. And these are dotted around about the same altitude and around what this has been interpreted as the elliptical outline of a sort of a collection of collapse structures where the edifice started collapsing in on itself throughout the lifetime of this volcanic center. So basically an incipient caldera formation. And so what I did want to point out, this is about 2 to 5 million years old in terms of dating, but it's really well preserved because it is such a dry area. It has seen some erosion from glaciation, but it is still one of the most well-preserved expressions of a magnetite-apatite deposit, and that's why it's really interesting to study. And in total, this actually comprises more than 700 megatons of high-grade iron ore. And so the question is, why can we even look at this, right? And what is the case is that this is owned by a mining company, but they're currently not mining it because it's too remote and too high altitude to be profitable. And which is really our luck, because when they were prospecting it, they made some nice cuts in the landscape in Laco Sur, which gives us some nice exposure, but then they left it in peace so we can go and study it as geologists. So that's a fantastic circumstance. So all of this taken together gives us a favorite genetic model of extrusion of an iron-rich liquid along collapse fractures of this volcano. But what is the nature and source of that ore liquid? Because it's such an exotic manifestation, some of the hypotheses that have been brought up are perhaps equally as exotic. So one of the hypotheses that has been discussed in the literature over the last 5-6 years or so has been that of bubble oxide flotation. This was essentially inspired by the process of industrial foam flotation, which is one way of concentrating ore minerals from away from gangue minerals in the mining industry. And in this case, you would crush the ore-bearing rock. You would suspend everything in some suspending fluid with the right properties and then blow gas bubbles around it through it. And those gas bubbles, they have a certain surfactant that gives them high surface tension, which picks up these ore minerals, binds them to the bubble walls, floats them up, and then it can be scooped off as a foam from the top. So the question is, can that actually happen naturally in a magma chamber? So the idea is that one study here by Jose Tomas Ovalle collected a lot of geochemical indicators of magnetites. So this is sort of a discrimination diagram with different trace elements in the magnetites. And they identified what they think or interpret to be a general trend of magmatic magnetites overprinted later by hydrothermal magnetites. And so they thought, well, if we have magmatic magnetite crystals first, they need to be harvested in some way and be brought to the surface. And so that's how they came up with this hypothesis of magmatic volatile fluid bubbles attaching themselves to oxide minerals and bringing them up. So the question is, does this actually work mechanically? And so there's been some experiments just recently published in 2019, which show that yes, in some circumstances, this actually works. And the process by which it does work is heterogeneous nucleation. So in these experiments, basically, these are iron-rich basalts that are water saturated, and they first form water bubbles, and then later, when oxides become saturated and crystallize out near the liquidus, they tend to like to nucleate on the bubble magma interface. because that's an energetically favorable position for them to be. And it can be the other way around as well. If oxides come out first and then the melt becomes water saturated, then bubbles like to nucleate on oxide surfaces as well. So in the left side of experiment, we can see some of these magnetites that have actually traveled to what was the up direction of the experimental capsule. So they formed aggregates, and they floated, small aggregates floated up in the capsule. However, they could calculate the approximate flotation rates given the duration of the experiments and the amount of magnetite accumulated. And they showed that it's actually quite a slow process, which requires hot, wet, and near liquidus magma to be resident in the magma reservoir for quite a long time. And we're talking about like upwards of 10,000 years, which is of the same time scale as the conductive cooling of a magma body of a typical size. So what about if bubbles were to grow and therefore have more buoyancy and be able to rise faster? That might also happen by bubble coalescent. But what we can see in this other experiment over here, where there's much larger bubbles to which smaller oxide crystals have attached themselves, is that actually with the growth of the bubble, the surface tension, which provides the force of attachment, actually drops as a function of the radius, the inverse of the radius, and therefore bubbles and oxides tend to detach from each other, even under very low dynamic conditions in an experimental capsule. So essentially, there's a double bind. If the aggregates are small enough, they are very well attached and they can float together, but they need a lot of time and near liquidus conditions, because as soon as there's too many crystals around, that would hinder that flotation. And if bubbles were able to detach, to coalesce and grow, it's much more likely that the oxide load will detach. An additional problem, which maybe we can go into if you're interested in the question time, is that if you did manage to form sort of a fluid magnetite suspension layer at the top, the question is, what would keep the magnetite from settling out if the suspending medium becomes basically a magmatic brine? There's such a large density contrast between magnetite and brine and such a low viscosity of brine that essentially one of these suspension layers, if it could be formed, would be very gravitationally unstable, and it would be highly likely that magnetite simply sinks back down into the magma chamber after this process. So interesting, but perhaps not for a Laco. So what else? What about this? Could this be a smoking gun? If you take andesite from the andesite deposits that are interbedded with the ore deposits on the Laco, and you look at them under the microscope, what can be seen is quite large and frequent melt inclusions, which look like this. They have these iron-rich globules that are embedded in a silica-rich matrix. If you zoom in a little bit more closely and you do some microprobe analysis, which some of my collaborators have done, and that was John Hanchar and Fernando Velasco, a colleague of Fernando Tornos, you find that these globules contain an iron pyroxene composition and also have some crystals of nanoscale magnetite in them. Whereas the silica-rich glass is actually a high silica dacite close to the boundary to rhyolite and has some CPX crystals in it. And this is all surrounded by a plagioclase crystal. This is very similar to a set of experiments which has been done also quite recently, which shows that there is spontaneous melt immiscibility in systems of similar composition to a Laco. What happens is that once plagioclase crystals grow in a reasonably iron-rich basaltic to intermediate magma, plagioclase, as you might recall, are rich in calcium, sodium, aluminium, and silica, but they don't like to take in any iron. And so basically, if you crystallize plagioclase, you push the iron away from that crystallization boundary and you form an iron-rich boundary layer around. And that can push conditions into a place where an iron oxide-rich fluid becomes stable as an immiscible fluid coexisting with a silica-rich melt. So that miscibility gap has been documented in a series of experiments. And so here on the x-axis, you can see all of sort of the proportion of all of the elements that tend to go into the iron-rich melt, which are titanium, iron, magnesium, calcium, and phosphate. And that gap opens up further and further with increasing water activity in the system, with increasing oxygen fugacity or more oxidizing conditions, also with increasing cooling and crystallization and increasing silica content. So this is reasonably well understood in experiment. So could this be an interesting hypothesis for the formation of a Laco-like deposits? As I said, some of our collaborators did analysis where they could actually measure the composition of the dacite to rhyolite matrix and these iron pyroxene compositions in the globules that are mixed together with magnetite. And all of this is plotted on a diagram where on the top are all of the elements that tend to go into the iron-rich melt. Bottom right is silica, bottom left is aluminium and alkalis. And we tried to see if we can connect the experimental data, which is the cloud of gray data, gray points in the background, with these new measurements by means of thermodynamic modeling using alpha melts, which is one form of the rhyolite melts software. So we entered a starting material similar to a low silica andesite from a Laco, and we observed along a cooling path from 1050 to 850 degrees that a silica-rich melt splits away from an iron-rich melt, and these have not identical but similar compositions to what is found in the experiments, and also similar to what we found in the Laco melt inclusions, although the iron-rich melt in these melt inclusions tends to be a little bit less iron-enriched, which could be simply because this most likely represents sort of an accessory form of that magma unmixing, which happened in these at a late stage in these melt inclusions, and that might be slightly different from a more large-scale magma unmixing process, which we're hypothesizing. And all of this happens at a total crystallinity of about 20 to 50%. So going from a suspension into a mush regime. So from this, we can formulate an updated genetic hypothesis, where we're positing that there is a melt separation event triggered by spontaneous magma unmixing, followed by the gravitational settling out of the denser, more iron-rich melt, which then would rise through collapse fractures, although the geometry of that process is a little unclear at this point, and then be in place as ore bodies anywhere from extrusive to shallow intrusives, of which there is also some borehole evidence at the Laco. So in the remainder of the talk, I'm going to go through these 3 points and show you how we address that with a combination of modeling tools and scaling analysis to see whether or not this process sequence is physically reasonable and internally consistent. So the first point we looked at was the process of melt separation. If we believe for now that this spontaneous unmixing can happen, and we are now faced with a situation where we have about 10% of this iron-rich melt, which has properties that are non-wetting towards the silicate crystals, a density of maybe around 3,500, so significantly denser than the rest of the magma, but a very low viscosity. That coexists in the matrix of a silica-rich melt, which is happily wetting the silica crystals that are around. Silicate crystals has a density that is about 1,000 less and a viscosity that is about 100,000 times more. So one of the questions to quickly address is, how do we know the viscosities of these melts? And some of the collaborators on that study, which you can read all about in Nature Communications, actually did viscometry experiments on compositions either taken from natural samples or synthesized after the analysis of melt inclusions that I presented before. And from this viscometry data, we were able to calibrate a temperature and composition dependent viscosity model specifically suited to that system. And basically on the y-axis, I'm sorry, I cut off the axis label here, is viscosity in Pascal seconds. And sort of this purple line extrapolated to 1,000 degrees over here gives us what I had said before, sort of something on the order of 1 Pascal second, whereas The original andesite is somewhere around 10 to 4 pascal second, and the rhyolite melt can go and exceed upwards of 10 to 6 pascal second. So thinking about the mechanical regimes of melt separation, we can basically plot this up in a ternary between the silica-rich melt, the iron-rich melt, and the crystals. So in moving inside the ternary, we'll be changing the phase proportions. And we can hypothesize that there are mechanical regimes where if it is dominated by a silica-rich melt and there's very few crystals and iron-rich melt droplets, then that's basically a suspension flow where the sinking of the droplets is resisted by the viscosity of the silica-rich melt that surrounds them. And as we're moving over towards more crystal-rich system, at some point they transition from suspension towards mush flow, and from mush flow towards porous flow, where the iron-rich melt is going to be increasingly interconnected into drainage channels, which can drain out by porous flow. And that's an interesting transition because in sort of mushy drainage systems or porous flows, the progress of the iron-rich melt is now no longer resisted by the viscosity of the suspending medium, but by the viscosity of the iron-rich melt itself, which I just argued is very low. So that could be potentially much quicker. And so we tested this in a scaling analysis based on some coefficient calibration that I argued for in my 2019 theory paper that I mentioned earlier on. So it would be too far to go into the detail of how we calculate this, but basically you're looking at color plots of the bottom bit of that ternary diagram I just introduced. So essentially going from a silica melt rich to a silica crystal rich system, and upwards would be enrichment of the iron rich melt. And we're looking at the characteristic speeds for magma or mush convection. If there's some natural density perturbation, the whole magma can convect. The speed of, and obviously convection has a tendency of keeping everything mixed. So that might be something that to a degree hinders the settling out of segregation. And then in the middle panel, this is the characteristic speed of melt segregation itself. And on the right-hand side is the compaction length. So that's basically the length scale over which a drainage system, if it exists, would arrange itself in the magma body. What we find going along this dashed path from basically 20% crystallinity where the melt and mixing sets in experiments to what is that? That's 50% crystallinity and about 10% melt fraction, and to possibly 10% iron-rich melt fraction, and to possibly more enrichment of the iron-rich melt towards the base of the magma chamber as it is continuously settling. We find that first, we find a system that is convecting with speeds of about 1 meter per hour, with droplets settling out at about 1 meter per year. And all of that happens on a length scale much less than 1 meter. So this, in this regime, the droplet settling might still happen, but it might not be the most efficient. And as we're pushing into the mush regime, mush convection gets much slower, so it gets a sluggish system, but the melt percolation speed is picking up significantly. So now they're on the same scale, and we start to establish drainage systems on a scale of meters to kilometers. And so from that, we can estimate that on a kilometer-sized magma body, which is reasonable for the size magmatic system we're talking about in Laco, the melt separation time would take somewhere between 0.1 to 1,000 years, so about 100 to 1,000 years, which compares favorably to the conductive cooling time scale for a body like that, which is about 10,000 years. So we would have plenty of time to actually extract the iron-rich melt on the time scale of that magma system, cooling, crystallizing, and figuring that melt immiscibility. So far, this works. But what about the collapse fractures? In the system that we just discussed, the iron-rich melt would collect towards the base of a shallow crust reservoir beneath the volcanic edifice. So how would we get collapse structures that connect sort of the underside, the underbelly of that magma reservoir with the flanks? And in order to assess under which conditions that geometry would be reasonable, we developed a finite element model of viscoelastoplastic rock deformation. And we seeded that with a weak inclusion representing the magma reservoir, which can be excited with a inflating or deflating rate. And the whole domain, including the volcanic edifice, which is bounded by a stress-free surface, can also be compressed and extended to mimic the impact of regional tectonics across the edifice. We ran that model for a lot of parameter variations, and this is just an overview matrix where on the vertical axis, models shown towards the top are on the moderately compressive tectonics, and towards the bottom is extensional tectonics. Towards the left is a deflating magma chamber, and towards the right is an inflating magma chamber. And what you can see is a range of different geometries, and the one that best supports the hypothesis that we aim to test is coming up in that red box here. So let me show you a little bit more detail on that. Essentially, what we find is that these conditions where we have faults extending sort of from the lateral extension of the magma body up to the flanks come up under moderate deflation and extension. And that actually fits really well with what we know from the geology or the conditions under which the emplacement at the Laco happened. First of all, this happens stratigraphically towards the end of the life cycle of that volcanic center, which indicates that it is most likely in a state of crystallization, cooling, and deflation, which would go really well. And incidentally, the deflation rate for that best fit scenario exactly matches the volume deflation rate given a reasonable cooling rate of that same size magma body and the thermal expanse, or the sort of the expansivity that we know from thermodynamic modeling that this system would have. So that fits really well. And the extension, as I argued at the very beginning, is also makes sense because there's this sort of this local crustal extension, which is indicated by the presence of these salares, which happen all around that area of Laco. This is robust for a range of depths of the magma chambers. It also is occurring for a spherical magma body, but not so much for a dike-like one. So it works best for an oblate to spherical magma body. It, however, does not work for combinations of deflation and compression or extension and inflation, which all form sort of fault patterns that are concentrated on the roof of the magma chamber rather than the lateral undersides. So, okay, so we think under the conditions that likely were present at Laco, we can get a favorable collapse fault geometry out. But we are left with the problem of getting a very dense, albeit low viscosity or melt through these collapse faults to the surface. So how would that work? So obviously in the finite element model, this was sort of a long-term deformation model where faults or collapse structures are basically just zones of long-term strain rate accumulation or strain rate localization. But in a natural system, this would be accompanied with some level of seismic activity. Like, for example, some of you might recall the caldera collapse of Kilauea crater in 2018, where like every now and again, there was one of these collapse events where the crater floor sagged down a few dozens of centimeters or half a meter or so, accompanied with a seismic magnitude of about 4 to 5. So what we calculated, given the outline of potential collapse structure from the interpretation of the geology, along with the lengths of these faults extending down to the magma reservoir, we can calculate that a slip distance of 1 to 10 centimeters would result in a moment magnitude of about 4.5 to 5.5. But because during one of these events, the roof of the magma chamber will be pressing down onto the deflating magma body, we can actually calculate from the volume shortening rate and the compressibility of the magma, what the pressure jump in the magma chamber will be. And it's on the order of 0.5 to 5 megapascals. And obviously, if you're increasing pressure and the fluid is around and the body is connected to permeable fractured areas, we can calculate what an injection speed might be if we're actually able to press some of that iron-rich, low viscosity melt into the base of these fracture zones. And we calculated a wide range of injection speeds, anywhere from a millimeter to upwards of 1 meter per second. But this is a reasonably fast process, so that can keep up with sort of the time scale of the seismic process. So what might happen next if we were able to, during one of these collapsing events, press some of the iron-rich melt into the base of these faults? Obviously, that melt would be flowing away from that pressure jump, and it would be flowing upwards towards lower pressurized areas. So it would undergo decompression. What happens if you decompress a melt, particularly in an arc system that is full of volatiles? There's potential for bubble exsolution. And if any bubbles already exist, these could expand as long as they're in the gas phase upon decompression. And so this exsolution and expansion of gas bubbles leads to a volume expansion, but everything is happening between the solid walls of fractures. So if you're expanding volume, that results in a pressure increase, and the pressure is going to push the flow towards wherever the lowest pressure is, which is obviously going to be along the fracture upwards. And so this would lead to a self-sustaining bubbly flow along the fracture, which is completely independent of the high buoyancy, the low buoyancy, the high density of the iron-rich melt, but instead is entirely a function of volume gain. So it's exactly the same as the Coke bottle, where it's the exsolution of gas that drives the flow to come out the top, not because Coke is in any way less dense than air. And so we did a scaling analysis of that problem, and we found that in very simplified circumstances, this can be described by an exponential growth of ascent speed along the fracture. And the e-fold growth length of that process, we could estimate to be about 100 to 1/10 of the fracture length. So that means that the exponential growth has a lot of space to basically grow along the fracture and potentially develop quite a lot of force towards the top. And for that, we found that it's sufficient if there's 0.1 to 1 weight% water dissolved in the ore liquid at depth. This is well in line with experimental evidence, which shows that these iron-rich melts, these immiscible melts, can have up to 2 weight% of water if they coexist with a water-saturated arc-type basaltic to andesitic magma. So again, we find that physically there's no reason why this could not work. And so that really brings me to the summary, where I promised you to give you some modeling insights into the process of iron-rich melt separation, collapse fracture geometry, and the process of how to actually bring a dense melt up to emplacement near the surface. So this all sounds very nice, but there are some really big and potentially troublesome open questions. One is that you can easily ask the question of why, if we think that this melt immiscibility occurs, are there so many andesites which clearly have not undergone immiscibility, except for, as an accessory process, preserved in melt inclusions? And there's various reasons why that might be. One would be the potential for crustal assimilation beneath a Laco, which might be assimilating things like sulfate-rich sediments, which are known to exist, or also ironstone rocks, which also exist in the basement underneath a Laco. And it could simply be a fact that the more the magma batches that have experienced the most assimilation are the most likely to undergo large-scale melt separation. Or it might be a function of progressive crystallizations, that the andesites that did come up have not yet crystallized far enough to trigger the immiscibility, and if they had remained in the subsurface, they would have gotten there as well. But to understand what happens, in particular also once you have this iron-rich melt produced, which initially, upon first immiscibility, only has about 30 to 40% iron, how do you push that further along to finally have something like 95% magnetite in the ore bodies? Is there some additional immiscibility or some fractionation of these melts? And this is really not understood yet, and some experimental petrology is needed. And then in addition, there's a lot of mechanical aspects of the problems I was showing now, like, for example, the problem of melt separation, which I just addressed with scaling analysis, but I'm sure there's a lot of interesting complexity in looking at the spatial flow patterns. And there might be a really good analogy to magmatic volatile phase segregation in felsic mushes, which is a really important problem for understanding volcanic hazards. And for that, multi-phase modeling is needed, which is one of the things that my group is actively working on. And with that, I'm done, and thanks a lot for your patience, and I'm happy to take questions.